Example 5.11 or 6.11 for the given textbooks. For details, please see the description below. The electric heating systems used in many houses consist of a simple duct with resistance heaters. Air is heated as it flows over resistance wires. Consider a 15 kilowatt electrical heating system. Air enters the heating section at 100 kilopascals and 17 Celsius with a volume flow rate of 150 meter cube per minute. If heat is lost from the air in the duct to the surroundings at a rate of 200 watts, we need to determine the exit temperature of air. In order to solve this problem, we're going to start by the energy balance. The rate of energy going in minus the rate of energy leaving the system is equal to the change of energy in the system. Since we consider the system to be a steady, this is going to be equal to 0. Notice we take the system to be this control volume, a piece of the duct, in which we have the electrical work going in, and then we have some heat that is being lost to the surroundings. We rewrite this to be E dot in is equal to E dot out, and then we simply said the amount of rate of energy going to be in is going to be what is being carried by the fluid, mass flow rate times H1, plus the amount of the power, the electrical power going in, is equal to the rate of change of the heat leaving, plus what is being carried out by the fluid leaving the system. Notice the information that we have is the power and the rate of heat change, and we also know the information of what the temperature goes in, so we could calculate the amount of enthalpy. What we need to look for is the amount of energy leaving, which is going to give us the exit temperature. So we rewrite this as the mass flow rate in plus the work, the power, electrical power, minus the change out is equal to the enthalpy, and we divide all this at the mass flow rate that we're going to have. So for us to be able to find the mass flow rate, we first need to find what is the specific volume, since the information that is provided is a volume flow rate. So to find the specific volume, we're going to use ideal gas law for air, and it's going to be V, and it's going to be at the entrance. It's going to be the constant, air constant times the temperature at the entrance divided by the pressure at the entrance. The constant for air is going to be 0.287 kilopascals meter cubed kilogram Kelvin. The temperature at the entrance, it's going to be 17 Celsius, which it becomes 290 Kelvin. And then the pressure at the entrance is equal to 100 kilopascals. This gives us a specific volume of 0.832 meter cubed per kilogram. Now, in order to find the mass flow rate, we're going to use the volume flow rate divided by the specific volume at that stage. So in this case, we have 150 meter cubed divided by minutes divided by the specific volume that we obtained in the previous step. And then we need to convert 1 minute into 60 seconds. So units cancel out, meter cube cancels, minutes and minutes, and then we ended up with kilograms per second. And then the solution of this is going to give us 3 kilograms per second. Now that we have the value of the mass flow rate, we substitute into this equation so that we could get the value of the temperature. Notice that for air, we're going to use the value for Cp to be 1.005 kilojoules per kilogram Celsius. To solve for temperature over here, please note that the enthalpy is exactly the same thing as Cp(T2). So this equation could be simply made into m dot H1 plus the electrical power minus the rate of change of heat out mass flow rate, Cp. That is going to be the final temperature. Then we replace the values. The mass flow rate is 3 kilograms per second. C, as we said before, H could be replaced as Cp times the temperature. So this kilojoules kilograms Celsius, and the temperature is 17 Celsius. The electrical power is equal to 15 kilowatts, and the amount of heat rate is equal to 200 watts. However, in order to maintain the units, notice that we have kilojoules, kilowatts. We need to also convert this into kilowatts, so it's 0.2 kilowatts divided by the mass flow rate, 3 kilograms per second, and once again the value of Cp, and that is equal to the final temperature. If we solve these numbers, we see that the final temperature is equal to 21.91 Celsius. Now let's double check that the units are correct. We want everything in the top to be kilowatts, so we have kilograms and kilograms cancel, Celsius and Celsius cancel, kilojoules per second is equal to a kilowatt. Now if we have at the bottom, we have kilograms and kilograms that we have, and notice that at the bottom we have kilojoules per second, which is a kilowatt. That cancels with all the units that we have at the top, and then at the end the unit that we have left is Celsius, which is the unit for temperature. Please note that the exit temperature of air is higher than the one entering the system, and this is due because the power of the electrical heater is significantly higher than the amount of heat rate loss to the surroundings.